This is the integrity recording for Nursing 227 over Chapter 17 in your Horntvedt book, which is Calculating Dosages Safely. And this chapter is about critical care dosages and calculations. So we have some objectives to this chapter, which you may review at your leisure. And basically we're going to look at different ways that we can quantify and set pumps for very specific amounts of medications. When you are caring for clients in this type of a setting, oftentimes they will have that number will be rounded to the tenths place, and so they maybe will be receiving 7.6 milliliters of a medication. And we also oftentimes will have, instead of milliliters per hour, we'll maybe be doing milliliters per minute. And again, it's for that very precise dose range that we want to obtain. So that's what we're going to look at now. We also will see that sometimes we will calibrate or titrate doses, and so that means that maybe you'll have a range that you want the client's blood pressure to remain within. And so what you could do then is obtain a blood pressure reading, and then you would either titrate your medication up or down to be in that range of what your doctor or healthcare provider has specified we would like those values to remain in. So most of the time when you're in this type of a care setting, you are going to see pumps used, and this is where we see the micro pumps used that can deliver those more precise amounts of medications, which would be by that first decimal again, or that tenths place. And so we would see a very precise measurement. If for some reason a pump wasn't available, this would be the case that you would grab the special tubing called micro drip tubing, and it's smaller drops, and this is so that if we needed to count, we would figure out how many drops we wanted per minute, and then the drops are smaller for more precise measurement, and so we would literally count the drops per minute in that drip chamber. Here's an example of what an order might look like, and so here we've got a medication that they're going to give over 3 minutes, and then we're going to get an infusion started, 5 to 10 micrograms per kilogram per minute. And so this is the type of problem we're going to figure out what you would set your pump to. If we have the client's weight in kilograms and we have a dosage of medication, what are you going to set your pump at so that you can deliver this dose of medication to the client? So a lot of times when we look at critical care calculations, we will use a drug weight, and so we will oftentimes use micrograms or milligrams, and then this will be again with either minutes or hours. And we use this because it's a little bit more precise than using a milliliter per hour flow rate, such as we have seen used, when we're infusing just normal saline or lactated ringers or more of your mainline solutions. These are very small or specific dosages of very potent medications, and so we want to make sure that we're giving the right dose. Well, in some facilities, we will see smart pumps used, and so that means that you may just be able to put in, the client's weight in kilograms. You would put in what the doctor has ordered. You would put in what your volume of solution is, and then how long you want the solution to be infused over. And so there are some pumps that will calculate this rate for you. Now we do, I'm based out of Williston, and our hospital does not have pumps like this. So it really depends on where you're working, and if you're at a more rural facility, which we definitely will have in North Dakota, we're definitely not going to have that all the time at our leisure. I know bigger hospitals do have the smart pumps. Okay, so when we look at what we need to know when we calculate, we need to know the amount of medication in the bag. This would be how the pharmacist has prepared it. And so this is kind of that married couple again. If your pharmacist sends you a bag of medication and it says it has 50 milligrams of medication and it's a 500 milliliter bag, you can't ever separate those numbers when we look at the equations coming up, because those numbers have to stay together. With that same thing being said, we also need to know how much fluid is in the bag. We know what our total volume is, and then we also need to know what our healthcare provider has ordered for the rate. Alright, so let's look at this problem here. A provider orders disopyramide to be infused at a rate of 0.2 milligrams per minute. The pharmacy provides the medication in an IV bag containing 125 milligrams and 250 milliliters of D5W. Calculate the infusion rate in milliliters per hour. Round the flow rate to the nearest 10th milliliter. So again, just like the last couple of weeks, you will have specific directions for rounding in every problem that you complete on Blackboard. And so let's just take a step back. These are maybe a little bit more lengthy problems, but they're not any more hard than anything you have been doing. By implementing the techniques you've learned with dimensional analysis, you will be able to very successfully solve these problems. It just might have a few more steps in it. So remember, our first step with dimensional analysis is always identifying what we're looking for. Our problem right here says calculate the infusion rate in milliliters per hour. So when we look at this, we're looking for milliliters per hour. Remember, when we have this slash here, this means that it's the division of this is what makes it an equation. So we know that we have to have milliliters over hours. So here's how we would start setting up our problem down here. We have milliliters over hours. Now, it would be wrong if we had milliliters per hour all in one line. By having milliliters straight line over hours, this is going to be your double check that when you bring hours into this equation to convert, you are going to have hours on the bottom, and this is your double check that you're setting up your problem correctly. So remember, when we have dimensional analysis, we start with what we're looking for, but then if you're sitting here thinking, how did she know to put 250 milliliters on top and 125 milligrams on the bottom? So here we have milliliters in the numerator of what we're looking for, or that top number of the equation. So that means that we have to have milliliters here. So oftentimes I will just start out my problem, I'll make my blank line here, and I will write milliliters. Then I go up to my problem, and I want to find information that I know about milliliters. So when I go up to my problem, I can look up here and I can see, let's see, we have 125 milligrams in 250 milliliters. Now in this problem, they're telling you that it's in D5W, but that's really totally irrelevant. That's additional information that has nothing to do with the problem. That would be something you would verify against your healthcare provider's order. So when we see this here, this 125 milligrams per 250 milliliters, what you need to be able to identify is that this is a marriage. This is what the pharmacist put in your bag of fluid, and this cannot be separated. So when we go down here, we know that we have to start out with milliliters because we have milliliters here. So we're going to put 250 milliliters on top, but since they're together and they're married up here, it has to go over 125 milligrams here on the bottom. So then we need to think about what our next step is. And so we always know our next step by identifying what we have ended off with in the last equation. And so when we look at that, we have milligrams here. So when we look at milligrams, we know that the next part of our problem, it gets a little bit busy now in this one, but our next part of the problem has to have milligrams here. So when we look back up to our problem, or when you look back on your PowerPoint, the next information that we had was that we had 0.2 milligrams per minute, and I will back up to that for you, and that is right here. So this is what that provider ordered. We have 0.2 milligrams per minute. Again, this is a marriage. We can't separate this. This has to stay together as an equation. Anytime that it's per, that we say the word per here, and we have that backslash, we have to have that together in one equation. So since we have milligrams here, we know we needed milligrams up here. We'll put our 0.2 milligrams over 1 minute, since we know that that has to stay together. That was our healthcare provider's order, and we can't change that. So when we look at the healthcare provider ordered something in minutes, and we're going to set our pump with hours, we've got to insert this conversion factor. So when we look down here to step 3, we have minutes as our denominator, or our bottom number. We know we have to go up to minutes here. This is so that we can cancel out the minutes and be left with hours in our answer. So we can go ahead and put minutes over hours, and then I will enter in my conversion numbers because I know that there's 60 minutes in 1 hour. The reason that I always label first is because if I sometimes if your brain thinks it gets a little bit ahead of you, I've seen that we'll have the potential to write 60 hours over 1 minute. And so to prevent that mistake, I know I've got minutes down here, I want minutes up here, so I go ahead and write minutes over hour, and then I enter in my numbers to make sure as a double check I'm getting my 60 and my 1 in the correct position. Now remember, how we deduce labels is by if it's on the top, we can cross it off on the bottom here. We can eliminate those. So we've eliminated milligrams, we've eliminated minutes, and then here as our double check, what we were looking for from our answer, we wanted milliliters per hour. And if you look here, we have milliliters on the top, and then we are left with hours on the bottom. And so when you would take your calculator and take 250 times 0.2 times 60 divided by 125, you will receive an answer of 24 milliliters per hour. So this would be the answer to our question. All right, so here is another example of the same style that I am going to leave you with the work for. And we are going to move on to 2 practice problems that you can do on your own. And then we're going to look at a different type of style of problem. And so here what we're going to do is we're going to calculate how the rate of our infusion should look based on the client's weight. And so we're going to need to know, in addition to the information in the last problem, we're going to also need to know the client's weight. And a lot of times in practice, this is what you will see. The healthcare provider will not always figure out the dosage. They have a set dosage that is therapeutic or that is treated for that condition, and then we need to figure that out based on the client's current weight. So again, just to highlight, anytime you're using a current weight, you're not going to ask the client what their last weight was. You're not going to ask them what they think their weight is. You are going to obtain a current and accurate weight on a scale that's been calibrated and has been zeroed, because when we're giving any type of medication, we want to make sure that we're using accurate data. So a provider orders methylprednisolone 0.25 milligrams per kilogram per minute for a patient that weighs 79 kilograms. The infusion bag contains 750 milligrams of methylprednisolone in 250 milliliters of D5W. Calculate the milliliters per hour infusion rate. Round to the nearest 10th mill. All right, so again, our problem tells us right here what we're looking for, and this makes it easy for us because when our problem tells us what we're looking for, or when we know what we're looking for, we can set up our problem correctly and we can take all the guesswork out of the math that we're doing. So we are looking for milliliters per hour. That means our first equation is going to look like this. Milliliters per is represented by this line here, and then we have hours. So we have milliliters as our very, very first numerator of what we're looking for. So that means we have to have numerator of our very first equation in dimensional analysis being milliliters. You don't know what this bottom is necessarily going to be. We're going to have to look up to the problem. And so right now I just have milliliters written on my paper. I'm going to look up and see what from my problem contains the label of milliliters. And I just have one thing, 250 milliliters. Okay, so I know that when I read my problem, the infusion bag contains 750 milligrams of this medication in 250 milliliters. So it looks a little bit different in this problem, but it's important that you're still able to identify that in this problem, this is the marriage. The marriage here is 750 milligrams in 250 milliliters. So when I go to my problem, I know 250 goes on top because I've identified that I need to have milliliters because I am looking for milliliters as the numerator of my equation. Since it's married, I know 750 milligrams has to go on the bottom. So when we look at our next step, then we need to see that we have milligrams here. We know that we need to go and put milligrams up here because that's what's going to eventually get canceled out. So then we need to look at our problem. And I'm going to back up to our problem to show us again, what does our problem tell us? We have 0.025 milligrams per kilogram per minute. That's what's been ordered. So when we look at this slide, what I want to point out to you is that you can never have two labels as your numerator or your top number. You can have two numbers or this slash of meaning per as your numerator. So you need to remember that when you have a 3-part label like this is, milligrams per kilogram per minute, you're only going to have one on top. So you're going to have 0.025 milligrams per, represented by this line, and then we can have kilogram/minute as our denominator in this equation. Now, we know that we'll be able to cross these out. So now we need to identify that we have kilograms and minutes here. Okay, what we're going to do next, what your book does next, is they identify that we should get rid of minutes. And so how we can get rid of minutes is by putting minutes up top, because that will allow us to reduce minutes. And then I will know that I'm looking for hours. So I know I can put hours down here. That can be done at, in a conversion step. And then after I write my minutes and my hours where I want them to be, now I'll go ahead and I'll add in my 60 and my 1. The next step then is we were still left with kilograms, and we have not reduced or been able to eliminate kilograms from our problem. So then, since we have kilograms on the bottom, we know kilograms needs to be on the top. Now, your book does not put an imaginary x that sometimes students will say I'm solving for x, and so anytime that there isn't this line under it, if it helps you to put the imaginary line to help remember that this is your numerator, because that's going to make a big difference in how you enter it into your calculator. So if you need to put this big line here, and if you need to put that you're solving for x, do that so that you can make sure that you're multiplying and dividing correctly. So how we would want to enter that into our calculator would be 250 times 0.025 times 60, and then we would go ahead and we would divide by 750. And I am entering this into my calculator as I was not speaking. So my answer is, I missed a step here as I was trying to catch up. So I want you to put this into your calculator and see what kind of an answer you get. All right, and it did, I wanted to know if it came out to exactly 39.5, and it does. Now this is where it's so important in Respondus that you guys look back to your question and we look at what the directions were. And so when we look at the problem here, our directions in this problem were to round to the nearest 10th mil. And most of the time with these critical care calculations, you're going to be doing the 10th, but you really need to pay specific attention to whatever your rounding instructions for that problem are. So this week in Respondus, it would say to answer the question using only the numbers, no label, and it would also note that you should not include, or that you should label, that you should round to the 10th. So we would enter this into Respondus then as just 39.5. The box on Respondus will be labeled for milliliters per hour already for you, so you won't need to do anything with that. All right, let's do one more like that. Provider orders dobutamine 2.5 micrograms per kilogram per minute for a client that weighs 70 kilograms. The infusion bag contains 500 milligrams of dobutamine and 250 milliliters of D5W. Calculate the milliliters per hour infusion rate. And our rounding instructions, which we probably will refer back to, are going to tell us to round to the nearest 10th. All right, so when we start with this problem, just like every other problem, we need to identify what we're looking for. And our problem says calculate the milliliters per hour infusion rate. You also, with the way that your math questions will be on your NCLEX and the way your math questions are this semester, you'll be able to look at the box label. And so the box that you will type your answer in will have a label after it, and it'll be labeled as milliliters per hour. Again, we can't put, one week I saw students doing this, and I'm going to attempt to write with this pen. I saw students doing milliliters per hour equals, and then they tried to put that over something. Oh, I don't know what they were trying to put it over. And you do not want to do that. So I'm erasing this because we definitely don't want to do that. This needs to be represented here by two different parts of the equation, and we will call them the numerator and denominator. So we have milliliters per hour. Since our numerator of what we're looking for is milliliters, we know milliliters has to go here. And let's look up to our problem. We are looking at this infusion bag. It's already been mixed. The pharmacist is telling us there's 500 milligrams of medication in 250 milliliters. D5W is actually irrelevant. Again, we would verify that it's in the right solution, but that's not part of the equation. So we know that 250 milliliters is married to 500 milligrams. So we can go ahead and put our 250 milligrams over 500 milligrams. Next thing then, what we need to do is look at milligrams here. We've got milligrams here. We don't have milligrams in our answer, so that means we need to figure out how to get rid of milligrams. When we look at our next step then, we've identified we needed to put milligrams up here. When you look back at the problem or the healthcare provider's order is talking about micrograms. So here is where I do know I can go right from milligrams to micrograms. I'd recommend you write milligrams first, and then you write micrograms. Then you should step back and look at the big picture, and here's where you use common sense to make sure you get the 1,000 and the 1 in the correct spot of the equation. And then our next step is outlined right here. Then we have micrograms, and we want to be able to somehow get rid of micrograms. And so if we put micrograms as the numerator of this next equation, that will get rid of that piece of data. Now we need to back up and see what from our problem has micrograms. And so when we look, we have 2.5 micrograms per kilogram per minute. Remember, we can have these two things together here. They were married when we looked at how they were identified in our problem. We have a marriage here, noting we have micrograms per kilogram per minute. So just like we couldn't separate these two pieces of information, the 500 and the 250, we need to keep this group together. This group of three labels needs to stay together. We'll call them triplets. The triplets have to stay together. So now we can decide if we want to get rid of our minutes first or our kilograms first. If you get rid of, it makes no difference to your problem, which you do next, knowing that kilograms is often over X. Sometimes it confuses students, and so I do often just say to get in the routine of eliminating minutes or hours first, so that you can continue on with your problem and filling in the dimensional analysis steps. But either way would give you the same answer. So we have identified we're going to get rid of minutes. So we've got minutes here, we're going to put minutes up here, we're going to add minutes over hours, and now I will enter in that there's 60 minutes in 1 hour. Our next step then is that we need to identify how to get rid of kilograms. We've still had kilograms left over down here, and our problem's not asking for anything with kilograms. So that means we need to somehow eliminate that label from our equation. So since kilograms is on the bottom, we need to have it on the top, and so we can put the line over X if that's less confusing for you. So in your calculator then, you're going to take 250 times 2.5 times 60 times 70 divided by 500 divided by 1,000. That will give us an answer of 5.25. We are looking for an answer that is rounded to the tenths place. So when we look at the tenths place, what we need to do is round accordingly. So we have a 2 here and we have a 5 in our hundredths place. So we would round then, since this is 5 or greater, we would round up. So our answer then is 5.3. All right, a couple more practice problems right here for you if you'd like to do more of those. Next, we're going to do some milligram and microgram per minute dosing questions, and it's really the same concept. I just want to walk you through a few more. If you struggle with math, I'm just really hoping that this repetition will help you as I walk you through the problem. So a nurse walks into a client's room and sees an IV infusion of lidocaine infusing at a rate of 12.4 milliliters per hour. The IV bag contains 500 milligrams of lidocaine and 500 milliliters of normal saline. Calculate the milligram per minute dosage that's infusing. Calculate the answer to the nearest 10th milligram. So this would be one way to double check a solution that's infusing, that it's infusing at the proper rate per your healthcare provider's order. So we are looking at the problem and it says calculate the milligrams per minute dosage. So let's look here. We've got milligrams per minute, and we know we need to start out with milligrams. You're always going to take that label from the numerator and pop it over. That's going to be your first label to your numerator of dimensional analysis. When we look at our problem, let's see what's married. The IV bag contains 500 milligrams of lidocaine and 500 milliliters of 0.9% normal saline. Don't let this confuse you. This would be the same as saying lactated ringers. This would be the same as saying D5W, D10. This is extra information in this word problem. You are going to be verifying this with your healthcare provider's order that you have the correct primary solution, but we aren't needing these in effect since it's a percentage and a number. Don't let this confuse you that you need it for your equation, because you don't. That would just be something you would verify against your doctor's order. Okay. So let's take a look here. And so we know that 500 milligrams of lidocaine and 500 milliliters needs to stay together because your pharmacist took this dose of medication and injected it into this much fluid, and that's your concentration, and we can't change that. So we have 500 milligrams over 500 milliliters. Again, we've got milliliters down here. Our answer doesn't call for milliliters, so we want to somehow get rid of milliliters. So we know we need to put milliliters up here. Our problem tells us that our pump is infusing at 12.4 milliliters per hour. Again, that's what your pump is telling you. You can't separate that or change that. You can't change hours to minutes because your pump is infusing 12.4 milliliters per hour. We're looking for minutes, so we're going to have to insert a conversion step, but we can't change this. This is what we see, this is what our pump is set at, and that's rock solid information that has to stay together. So then we can go ahead and we can cross out our milliliters like we've done here. Now we have hours. We know our problem asks for minutes. So here we're going to take hours from the bottom and we're going to put it up top. We know hours can then be converted into minutes. We can then enter with our common sense knowledge. We know that there's 60 minutes in 1 hour, but by entering the label first, it helps us to take the guesswork out, and it helps us to remember that the 60 goes on the bottom of this particular equation because it's not going to be the same. It depends on what information you're given and what you're looking for. So then in this problem, we would take 500 times 12.4 divided by 500 divided by 60, and we get an answer of 0.2. So it happens to be rounded nicely to the 10th like we wanted it to be, and that's what our directions told us. So that works out perfect. You also want to make sure that then if your infusion is running at 0.2 milligrams per minute, you can verify this with the provider's order and that is a dose that's within range and that's accurate. So sometimes we are going to need to I'm going to let you, here's another practice problem. I'm not going to walk you through this one. I think you'll be able to get this. There is work on your PowerPoint. And then we've got some more practice problems here that you can do to get ready for the quiz. Okay, titrating is what I want to go to next. So titrating might be when your provider will order a medication to be infusing between 16.4 and 18 milliliters per hour. And so what you're going to do then is titrate this based on some type of assessment value, whether it be blood pressure, whether it be blood sugar, or anything in between. And so our example for this problem would be if a healthcare provider writes an order to start dopamine at 5 micrograms per kilogram per minute IV. The dopamine drip is to be titrated in 5 micrograms per kilogram per minute increments up to 20 micrograms per kilogram per minute. We want to titrate medications like dopamine that are used for the heart because it can be too drastic of a change, or it can cause too rapid of a change in vital signs if we would just all of a sudden start them on 20 micrograms per kilogram per minute. So we'll start them at a lower rate, and then you're going to slowly titrate them up or increase their rate. And then our doctor says that the patient's systolic blood pressure should be kept greater than 110. We know that the client's weight is 73 kilograms, and then the pharmacy that the bag that they're giving us contains 800 milligrams of dopamine and 500 milliliters of D5W. So we want to calculate the milliliters per hour flow rate range, and so anytime it says range, you're going to be entering two numbers. And so when we look at this, our range, or also worded as titration, our range is going to be 5 micrograms to 20 micrograms. So we're going to have two different numbers, and then any numbers in that range would be acceptable. And then we're going to round to the nearest tenth. All right, so when we look at this problem, we're looking for milliliters per hour. All right, so we know that we have to have milliliters here. When we look at our problem, the bag of solution from the pharmacy has 500 milliliters in it, and the dosage is 800 milligrams. Again, I know 500 goes on top because we're solving for milliliters per hour, and we have to pull this milliliters over, and that's what we have to start out this problem with. That's how we can pretty much be guaranteed to get our dimensional analysis questions correct. So we've got milligrams down here. We know we need to put milligrams up here. Now, when we look back at our problem, though, our problem's talking about micrograms. So we know we're going to have to convert, but that's okay. I can convert from milligrams to micrograms in one step. I will go ahead and enter in my label first, milligrams over micrograms. Then I will sit back, reflect, and enter my 1 milligram equals 1,000 micrograms. Now we have micrograms at the bottom, and so we want to go ahead and put micrograms up top here so that we're going to be able to cancel those out, just like we canceled out our milligrams. And so our problem tells us that the bottom of our beginning flow rate is 5 micrograms per kilogram per minute, and we're trying to find the mils per hour flow rate. So we need to convert minutes to hours. This has two different conversion factors. So not only are we converting micrograms to milligrams, but we're also converting minutes to hours. So we know that we can put minutes up top and then label with hours, and then I'll add in my 60. Because I know that there's 60 minutes in 1 hour. Then when we look at this step here, we were left with kilograms, and we need to reduce or eliminate kilograms because our answer is not asking for kilograms. Our answer only wants milliliters per hour. This is another way you can step back and review your work and identify if this information in the problem was extra or if it's needed for your calculation. And sometimes you are going to have extra information in problems, and so it's important that you're able to deduce the information that you need and the information that's extra. And so we don't want this kilograms left here because our problem doesn't ask for kilograms. So here's where we know then we need to enter kilograms. Even though it was back here and we did our conversion in between, since kilograms is on the bottom, we know that we need to continue with kilograms then on the top. Again, you can do over X if that helps you to keep it a little bit simpler in your mind. So then we're just going to put the numbers in our calculator. We've got 500 times 5 times 60 times 73 divided by 800 divided by 1,000. And that gives us an answer of 13.7. And so that didn't even need to be rounded any further because our directions told us to round to the nearest tenth. All right, so now this is just the beginning of the problem though, because remember, we were doing a flow range. And so the bottom range was with 5 micrograms, okay? But the upper range is going to be with a different number. So when we look back at our problem, the healthcare provider said 5 to 20 micrograms. So we're going to set this problem up exactly like we did the last problem. We're just going to change this step to 20. So now our answer is 54.8. And when you would enter this into the computer, your dosage range then would be 13.7 to 54.8. What you will see in questions on the math quiz would be the client's pump is infusing at 37.2 milliliters per hour. Is this within the titrated therapeutic ordered range? And then you would be able to select yes or no. Okay, so here we have some additional practice questions for you. And then we have another example. One of the things I want you to do this week, I think it's really important that you take advantage of the practice worksheet that I have posted in your course shell. Under announcements, I have all of the math worksheets for the remainder of the semester posted. And I'd really like you to take advantage of those worksheets because that will help you. Sometimes in the problems on your quiz this week, you're going to be given a doctor's a range of a medication dosage. And then you're going to be told what the drip rate is. And the question's going to be asking you what that drip rate is within micrograms per minute. And so you're going to have to take, a drip rate, and you're going to have to identify if it's within the range, in that therapeutic range, and you're going to have to calculate what it is. So I think it's important to take advantage of the practice worksheets. All right, and then we've got a couple more equations here that you guys can practice, and some more practice questions here. We do have definitely some high-risk medications, heparin or diltiazem, even insulin drips, and so a lot of times we will use medications like that on special pumps that have orders built into them, and that's kind of also used as a double check because errors can happen, and so our technology that's come out with pumps does help to make the errors less within practice. And so you want to just make sure that you kind of know the normal values, and you would learn this as you worked in practice, but what would the rate be you would expect of a cardizem drip in the ICU and things of that nature, so that if you got an answer that was much too large or much too small, you would have those common sense skills to question that and to think, this doesn't seem right, I need to ask someone else for further clarification. And then here's just an example of what a medication order might look like, or what we might see on one of those high-risk medications. And it's got some criteria for when we would discontinue the infusion, and then when you would call the doctor as well. And so this is pretty standard, definitely something you'll probably see in practice. Let me know if you have any questions about this lecture, and I would be happy to help you. Have a great rest of the day.